Let's take a look at vertex form compared to the vertex formula when referring to quadratic equations. So first, in general, whenever you are asked to get an equation into vertex form, you are being asked basically to get this equation into shifted form. Basically the form that would show the transformations that had occurred to y equals x squared. So vertex form in general will look like x subtract some h, where h is a number, all in parentheses squared, plus k, where again k is a number. H and k represent some shifting that have occurred to this quadratic equation. Also, please remember that because y equals x squared begins at the origin, this shifting, notice h here is positive because on the inside the shifting is exactly the opposite of the way it actually would have moved. This h and k will also happen to be the vertex, because the vertex will be the exact numbers as to what the shifting was. Over here, however, on vertex formula, this is kind of a tricky little vocabulary thing. So when it says formula, it's actually a situation where generally you're being asked just to solve for a vertex. So the idea is the vertex formula is that hk, the actual vertex, is equal to, and I'm going to write this as h being the x coming first, comma the y. So here notice I'm using ordered pair notation. So negative b over 2a. That corresponds with h, or some people might even say that corresponds to what the x part of the vertex would be. This is how some people might actually think of this. And then of course the y part that goes to this vertex would be the function, where you go back and substitute in whatever that number was. So here we use function notation. Whatever the number was that you got for the x part, substitute it into your function to get the y number that goes with it. So please notice vertex form wants an actual shifted form of the equation, while the vertex formula is referring to this negative b over 2a when you're solving only for the vertex. You can still get the vertex off of this shifted form, the hk, but again, just be aware that directionally speaking, there are two different outcomes. Now let's look at some examples. Okay, the first example. Given the quadratic equation x squared subtract 6x plus 5, let's get this into vertex form. So I'm going to say write in vertex shifted form as the directions for this problem. In order to do this, basically we complete the square. So the first thing I'm going to recommend is to make this look easier. Instead of writing g of x, which is actually the name of this function, I'm going to replace that with a y so that I can complete the square maybe in a slightly cleaner method. So y is equal to x squared subtract 6x plus 5. Remember that as we complete the square, we have some standard steps that we like to follow. Basically get x stuff on one side, get the other stuff on the other side. Since I have y on the left, I'm actually going to take this 5 and move it to the left with the y, leaving the x stuff on the right hand side. So that's going to give me y subtract 5 equal to x squared subtract 6x. Also, for prep work with completing the square, once we have x stuff alone and everything else on the other side of the equals, we also need to look at the x squared term and make sure that there's a coefficient of 1 here. Because we have a coefficient of 1, we are pretty happy, meaning we don't have to divide anything out in order to make it a 1. At this point, we've prepped this problem so that we can complete the square. So what we always do is take this the coefficient off of our center term, the x, which is negative 6. I'm going to write 6 since we've discussed before that the negative doesn't make a difference since we're about to square this. We're going to take 6. We always half this, and we always square this. So in other words, here we have 3 squared. I'm going to add this number here to give me a perfectly square trinomial on the right-hand side. And then, of course, if I add something to the right-hand side of my equation, I must also add it to the other side. So here I'm going to also add on the left 3x squared. Excuse me, 3 squared. Okay. Now, continuing to complete the square, we can actually factor the right-hand side in one step. Basically, we take the x, we take the negative, and we take the 3 from this quadratic equation. So we're going to say here, x subtract 3 squared is the factored representation of this original quadratic that we have. Now I'm going to say equals. To clean up the left-hand side, please notice that 3 squared is a 9. And so we have 9 minus 5 on the right-hand side. So I'm going to rewrite that as a 4. So we have y plus 4 being the simplification that we get when we put the 9 and the negative 5 together. We get the positive 4. So now let's subtract 4 from both sides to get y alone. So this right here is the solution to writing this equation in vertex form. Of course, putting a g of x on the front of it would also be nice. It would make it match the original a little better. Let's continue this example now and discuss the properties and the importance of writing an equation in this form. What can we tell quickly now from this form? Okay, so here again we have our equation written in vertex form. And there's some really quick things that you can see off of this version. We can actually see exactly how the original y equals x squared, remember that the toolbox function y equals x squared is the one that has now been moved around to give us the minus 3 inside parentheses and the subtract 4 on the outside of the equation. So we can see the transformations that it's gone through. We can see that it's gone to the right by 3, down by 4. More importantly, we can actually see the vertex very quickly. The vertex, remember, is going to be hk, where we take the opposite of that 3, a positive 3 for the h, or the x part of the vertex, and k is going to be the same, negative 4, because it was shifted down by 4. So we can get the vertex off of vertex form very quickly, which is nice, in addition to seeing how exactly the equation was shifted. We can also get the axis of symmetry. Basically, this is the line that if we were to graph this equation, which we will also do, where we could divide this thing straight down the middle vertically and have symmetry. This will occur always at x equals, and it will be x equals 3 in this case, since that is the x part of my vertex. So let me show you what I mean now regarding the picture. Vertex form is especially nice for graphing if we are not going to use technology. Because what we can do is move over from the original origin point to the right 3. 1, 2, 3, down 4, 1, 2, 3, 4, to this point. We can see from the front of this, there's not, well, actually the original and the front of this vertex form, that it's positive. You would have a negative either here in front or here in front of the x squared if it had been flipped down. So we can see that it's still pointing upward. We'll discuss those x-intercepts in just a second. But the idea is that in general this thing's pointing up. We know the vertex is at 3, negative 4. The axis of symmetry would be a vertical line that cuts through this thing at x equals 3. That's a little symmetry line for us. Again, we also said that up and down is determined based on the coefficient of x squared. A lot of times notated by an a. In this case, if it had an a that had been flipped or even multiplied by a factor, you'd also see that outside of the parentheses on your function. But again, we have a 1 here. See, a 1 there and a 1 there. So that means it's up and it has not been multiplied by any vertical factors. No stretching or shrinking it vertically. As far as getting these x-intercepts, if we wanted them, what we can then do is go back and solve for those by hand. Okay, so here we've solved this equation and gotten it into the proper form. We've noted some things. You may also want to notice things such as domain and range. The domain on this can easily be spotted whether you've actually graphed it or whether you've just written out some of the basic properties that you get from looking at it in this form. The domain is everything side to side, so we have negative infinity to infinity. The range is going to be from this low point here of -4, so that's where the -4 really comes in, including that, of course, since that's a closed circle, and up to infinity. Okay, on this example, we're still being asked to write this equation in vertex form. So our objective is going to basically be the same. We want to complete the square, and then after completing the square, solve for y equals, and it will naturally be in this vertex, also known as shifted form of the equation. So I'm going to again write y equals in place of the p of x. And at the very end, we can go back and put p of x in for the name of this function. This just makes it look a lot nicer in my opinion. Then what we can do is move this 3 over because we do need our x stuff alone. So that means we have y plus 3 equals -2x squared subtract 8x. At this point, it's slightly different than what it was on the last example. Slightly different, I mean, because if you look here at x squared, we actually have a coefficient on this x squared of -2. So we are required to have a 1 on x squared in order to complete the square. So we're going to divide every single piece on both sides of the equals by this -2. This will give us y over -2 plus a -3/2 equals x squared plus 4x. Now we've prepared this problem for actually completing the square. So we'll take this term, the 4x, and using its coefficient 4, we always divide that by 2 and we always square it. So I'm going to say divide by 2 squared. That's the same thing as a 2 squared. So I'm going to put plus 2 squared on the right. If I add it to one side, I must also add it to the other side. So plus 2 squared also on the left. This is important because now we can actually factor this in one step by taking this x, this addition symbol, and this 2, and putting those into parentheses. So x plus 2 squared we have on the right-hand side. On the left-hand side, we have, let's see, first we have a 4, subtract 3/2. Okay, so here's the equation. I've actually just pulled it up on the board. Also, please notice that the 5/2 on this is positive on our answer. So we will subtract 5/2 from both sides of the equation. Now we have y over -2 equals x plus 2 squared minus 5/2. We still want y alone, so we will multiply -2/2 to both sides of the equation. Remember when doing that you do want to hit every term on both sides of the equally to keep this equals statement true. What that means is that the x plus 2 squared will get hit once in the very front with multiplication of -2. You do not distribute this -2 because there is a squared symbol on front. So you simply write, hey, multiply that by -2, but do not attempt to put it into the parentheses. And then the other piece that we still have to multiply by over here on the right is that -5/2 by the -2. That will make the -2's cancel. It will also make the negative here turn to a positive, and these 2's will also cancel. So now we have y equals -2 times x plus 2 squared plus 5. This is our equation written in vertex form. So let's talk about the things that we can see from this equation. First of all, we can see how the original y equals x squared would have been modified or transformed. So the idea is that y equals x squared, to give me this new equation, would have had several things done to it. First, we'll say inside the parentheses that it was moved to the left by 2. It also was stretched by a vertical factor, this is kind of a review, of 2. It also was flipped over the x-axis, and it was also moved up by 5. In other words, we could quickly sketch a basic picture of this equation without really even using our calculators. So this is a nice analytical approach that gives us good pictures and lots of information quickly. So the idea again is that vertex, by the way, the vertex we know would be -2. It's the opposite of the 2 you see here. And it's always going to be the same as that up 5 movement. So the vertex is -2, 5. Meaning that we're going to go, let's see, 1, 2 to the left, 1, 2, 3, 4, 5 up. We do know this thing is going to be a little wider than normal, but again, this is a rough sketch. We also know it's pointing down. If we were making a better sketch, we would actually solve for those x-intercepts so that our graph would look better. We would also place the y-intercept on the picture, which, by the way, the y-intercept should be, mine's not correct actually on this rough sketch, because the y-intercept should be right there at -3. When zeros are put in place of the x, that's when we get the y-intercept. But again, here our objective is just to get this into a nice shifted form so we can discuss characteristics like the vertex, get a basic kind of understanding of the picture, and then also talk about domain, range, and that kind of thing. The domain here, of course, is -infinity to infinity. The range here begins up here at 5. Actually, it would begin at -infinity and go up until 5. And our axis of symmetry would be x equals -2. Okay, part 2 of this lesson is using the vertex formula. So here we have the same 2 examples that we just now rewrote by completing the square into vertex form. So the other objective that I could have asked you for here would be to get the vertex from these equations using the vertex formula, which we said at the start of this video. That's slightly different as far as the objective for what you want to do. So remember that the vertex formula is basically x equals -b over 2a. So here on the first one, g of x, to get the vertex of this, I'm going to begin by getting the x part of the vertex. X is equal to, we said -b, so the opposite of 6, or the opposite of -6 is 6, divided by 2, multiplied by the a right there on the x squared is just a 1. So we are getting 6 divided by 2 is 3. That's the x part. Now to get the y that goes with this x of 3, we'll take the g function, plug the x value into it to get the output. So here we have 3 squared, subtract 6 times 3 plus 5. This will give me -4. So my vertex on this equation is 3, -4. We can also see from this original equation that a is equal to 1. So another way of taking this vertex and going further, the full answer here is right here. The vertex is 3, -4. But if we wanted to be extra fancy and write this in shifted form, we could actually switch back now to the vertex form, the y equals equation, very quickly because we have the vertex and the a. This is another way that we can approach getting the vertex form without having to complete the square. It's a good way to check ourselves from the process that we used earlier, in this example earlier today. So g of x is equal to, we know the general vertex form would be the a in front, which in this case is a 1, parentheses, x, opposite of what we have here for the actual x value on the vertex, so -3 squared, and the y always stays the same. So again, our objective here for the vertex, using the vertex formula right there, was right here. I've circled it. But if you want to be extra fancy and get the vertex form, you can still connect those ideas and get back to that nice shifted form that we were discussing earlier. Now for p of x. Let's go ahead and get the vertex on that one. So here, x is equal to -b, that's going to be the opposite of -8, which is a +8, over 2 multiplied by the a, which is a -2. That's 8 divided by -4. So we are getting a -2 there for our x. Now we'll take that -2 and put it back into our equation in place of x. so that we can get the output that goes along with the x we've just solved for. Here we get a positive 5. So our vertex, our solution for this objective, is -2, 5. So we could stop there. If we wanted to go a little further and kind of reiterate the idea of vertex form for this can also be found from looking at this vertex, and of course from noticing that the A, this time is not actually a 1, the A is -2. So A is equal to -2, because what we can do here is say y is equal to, or I guess better yet we could say p of x is equal to, let me change that. We can say p of x is equal to, we will take our A from the original, then in parentheses we use x, the opposite of this x value here, which is a +2 squared, keeping that +5 positive on the outside, and there we have vertex form using a difference.